Okay, today we are going to discuss falling bodies. If tradition serves correctly, falling bodies, a falling apple in particular, is what got Isaac Newton interested in calculus and motion and all the things that have led to differential equations. So we're going right back to the beginning here. Speaking of Newton, we're going to be using his three laws of motion in order to be able to solve this problem. The first law of motion is that well, let me take the second law of motion. The second law of motion is that the sum of the forces acting on some body is what causes it to accelerate. Okay, if you look at all the forces acting on something and you look at them all together and they're all vector forces, so they're maybe acting in different directions, but you take the sum of those, that is what causes an object to change its velocity. If there were no forces at all acting on a body, an object would just continue moving in whatever velocity it's moving at. If it's still, it will remain still. If it's moving like this, it will continue moving like that. It's only because of air resistance or gravity or something else that it causes anything to slow down. So that's the second law of motion of Newton. Okay, and so here A stands for acceleration, and this is the sum of the forces, and it's the mass of the object which is the proportionality constant. In other words, if you double the mass, if given the fact that you have a certain force acting on a body, if you double the mass, then the acceleration will be half as much. Or if you, yeah, that's an easy way to think about it. Okay, so if I push hard on two things and one of them is twice as heavy as the other one, then the one will start moving at twice the acceleration as the other one. So if you have an object that is just suspended in the air and you drop it, then the main force acting on that body, the main one that we're going to look at right now, is just the force due to gravity. And the force due to gravity is also proportional to the mass of it. Okay, so here you have some sort of a mass right here, and we'll let up be positive, and we'll let down be negative. And the force acting on this thing is going to be negative mg. Okay, so it's negative because it's pulling it down. So we'll take all these constants to be positive quantities, and so if I want there to be a negative there, I'll bring it out here explicitly as a negative sign. So the force acting on this thing is basically its weight, and the weight is the mass of the thing times the acceleration due to gravity. The constant is g. So we'll see this as we go. It'll make more sense as we kind of pull this together. So there's the weight of the object. That's the weight. That's the force at which it's being pulled down. So we're going to assume that that's the only force. Okay, we're going to keep this as simple as possible and think of that as being the only force on the object, and then the sum of those forces, in particular that one force, is what accelerates the object. Okay, is what pulls it down. So in other words, negative mg is equal to m, and the acceleration is the derivative of the velocity, so we can write dv dt, and so we can divide both sides by m, and we get dv dt is equal to negative g. And as I say, that constant at the Earth's surface, g is equal to 32 feet per second. That's the acceleration due to gravity. So this is something which is just seen. If you drop something from a high tower, the rate at which the velocity changes is constant. It's going to start at 0, and then a second later it's going to be going at 32 feet per second, and 2 seconds later it's going to be 64 feet per second. It's going to keep speeding up. So there is the acceleration due to gravity. Okay, I want to follow what I'm doing in the book. So if this were the only force acting on the object, then we could take the antiderivative of this. The derivative of this side is going to be v. The derivative of this side is going to be what? This is just a constant, so it's going to be negative gt plus some initial constant. I'm going to call that constant v naught. The reason I'm going to call it v naught is notice that stands for the initial velocity of the object. So this is v of t right here. This is the velocity at time t. And at time t equal to 0, this will be 0. So at time t equal to 0, the velocity will be v naught. So v naught is the initial velocity of the object. That's why I call it v naught. So there it is. And then if you remember what you did back in Calc 1, you can go even one step further and you can say, oh, okay, the height of the object, let's let y stand for the height. So the height of the object is going to be dy dt. That's the position, and the derivative of the position gives us the velocity, which is negative gt plus v naught. And so now I can take the antiderivative of that, and I get y is equal to, what's the antiderivative of this? You add 1 to the t, it's going to be t squared. Divide by 2, it's going to be negative g over 2 t squared plus v naught times t plus, let's call it y naught for the initial height. So there's the height of an object, given the fact that the only force on it is the force due to gravity. And as I say, given that this is 32, if you stick that in there, you're going to get y is equal to 32 over 2 is going to be negative 16 t squared plus v naught times t plus y naught. So there's the height of an object, starting at height y naught and starting with velocity v naught, and the height of the object under the influence of gravity at the Earth's surface. So one thing I did back in Calc 1 was I said, okay, assume you throw something from a tall building and you throw it, say v naught is 64 feet per second. That's your initial velocity. And suppose you're throwing it from a building which is 80 feet high. So this is 80 feet high, and you throw it up, and the question is, when will it hit the ground, things like that. How high will it go, all those kinds of things. So this is one of my favorite problems in Calc 1. And so if you were to do this one, you're going to get negative 16 t squared plus 64 t plus 80. And then you can ask all sorts of questions. When will it hit the ground? So to find out when it hits the ground, you set that equal to 0. I won't go through all this. This is kind of a parenthetical remark, and you're going to get t is equal to 5 just by solving this quadratic. You can, by the way, notice I chose these numbers because you can factor negative 16 out, and you're going to get negative t squared minus 4t minus 5 is equal to 0, and that factors into, I guess I am doing it for you, t minus 4, or rather t, let's see, did I do that right? T minus 5, rather, t plus 1. Agreed? So that gives you this, and so that tells you that at time equal to 5, it hits the ground. And if you want to know how high it goes, then you want to know when will the velocity be equal to 0. So it starts here, it goes up, comes back down. At that highest point, the velocity is 0. So to get the velocity again, here it is. You can go ahead and get it by just taking the derivative. V of t is going to be what? Negative 32t plus 64. That's the velocity at any time. If you set that equal to 0, you're going to get t is equal to 2, and that tells you at time equal to 2 is when it hits the highest point. You can stick that back in here and find out how high it goes and things like that. Okay? So that's all a big parenthesis. Okay? That's all the stuff we did back in Calc 1. Okay. But now, we're gonna look at this a little bit further and say, wait a second. This model, just like when we looked at the model of population and we said, well, if you look at the simple population, this mold is going to eventually fill the universe, and of course that's not true. And similarly, according to this model, even if there were no Earth to stop it, this thing is just going to keep going faster and faster and faster. It's going to keep increasing by 32 feet per second every second. It's going to be going faster and faster all the time, that's just not what happens to a falling object. If you drop something like an eraser from even the top of my house or something like that, it'll start going, but eventually it's going to reach a terminal velocity. It basically won't go any faster than a certain speed, and it'll just kind of keep falling at that speed. And so we apparently need a better model that takes that into account. Okay, so let's erase all this, and let's ask, how can we improve our model? What can we do to make our model more realistic? Okay, let's go all the way back to this, I guess, and say, what other forces are acting on this object besides gravity? And hopefully you say, oh, well, the other obvious one is air resistance, right? This thing is going through the air. And so that's another force acting on it. And so if we were to drop it, then let's look at the forces. It's going to be negative mg, that's the force due to gravity. If the object is moving down, then the force due to friction is going to be up, agreed? If this thing is moving down, the force due to friction is going to be up. So it's going to be up, and it's going to be dependent on the velocity. If you are in a boat and you put your hand in the water, you can feel the force of the water against your hand. And if you're going faster in the boat, the force due to water is faster. If you're in a car and you put your hand out of the car, you can feel the force due to the wind on your hand. And the faster you go, the more the force is, okay? I sometimes tell my classes that when I was on a Delta flight from San Francisco to New York, I wanted to test it, so I punched a hole in the window and stuck my hand out, and I noticed that there's a whole lot of force, and I also noticed that I'm no longer allowed to fly on Delta. It's just a joke. But my hand wouldn't have lasted very long with the force due to that wind up there, okay? So anyway, let's think it through here. So if you are falling, if the velocity is down, if the velocity is negative, then we want the force to be positive, agreed? So if this thing is a negative number, then I would want a negative here because the velocity is negative, and then this is negative, and those two negatives will make it a positive, so there's going to be a positive force, and that force is proportional. We're going to assume it's proportional to the velocity. As the velocity increases, so does the force in proportion. And so those two things together are the two forces, and so that's going to be the mass times the acceleration. Okay, and of course the acceleration is just the derivative of the velocity again. Okay? So now we can solve this thing for dv dt, and we get dv dt is equal to, I'm going to divide through by m, and I'm going to get negative g minus k over m times v. So agree with that? Does that all look good? Make sure that I have the same thing here. Okay. Okay. So there's a differential equation. That's a better model than we had before because it takes another force into account as well, the force due to friction. Question is, can we solve it? The other one was very easy to solve. Can we solve this one? Well, yeah, we can. Notice that it is separable. We can divide through by this whole thing here, and so let's go ahead and solve it. Okay, And so let's go ahead and solve it. And so we'll solve it by getting all the v's over to one side and the dt's on the other. So I'm going to write it like this. dv divided by, let's see, I'll write it like this. K over mv plus g. I'm going to bring that all down. Notice I'm keeping the negative there. There's no reason to make this any more complicated than you have to. So this is going to be equal to negative, and I'll bring the dt up, dt. See that? So there it is. And now, I think this is one of your exercises actually. But let's go ahead and this is exercise 281 in our current textbook. And so let's go ahead and solve it. And so I'll help you with this one. So we're going to take the antiderivative of both sides. Okay. So how can we solve it? Let me make that a little bit tighter right there. Okay. So how can we solve it? Well, this side is easy enough. That's just going to be negative t plus c. Okay. What about this side? Well, notice that I have pretty close to the derivative of the bottom is up on top here. If I wanted to, I could make myself a u substitution and let u be equal to this whole thing and do it formally like that, but it's easier. I told you I did this the other day. All I'm gonna do is I'm gonna just make sure that the derivative of the bottom is up here. So the derivative of the bottom is what? This is my variable right there. So the derivative of the bottom is just going to be k over m. So I want to have a k over m up here. So I'll just stick it there. Okay? Well, I can stick it there as long as I don't change anything. So I'm going to put a m over k outside. Agreed? M over k times k over m is just 1. So I haven't changed anything. But now I do have the derivative of the bottom is up on top. So now it's all the easier. If you want to, you can just let this be u, and this is all going to be du. But the point is I can do it in my head. You work through the details if you need to, but now it's just going to be the derivative of the bottom is up on top. So this is going to be m over k times the ln of the bottom. K over m v plus g, right there. And then we're almost done, of course. Now we can multiply through by this. And we're going to get ln of k over mv plus g is equal to, if I multiply by k over m, I'm going to get negative k over mt. This is a constant. If I multiply a constant by just some other constant, it's just going to be another one. So I'll call this c1, and then I'll just call this c. Okay, so it's different from this, but the point is it's still just a constant. So that's all good. And now I can take e to both sides. And if I take e to both sides, I'm going to get k over mv plus g right there. And then I'm going to get, we've done this a bunch of times now, so watch me carefully, e to the negative k over mt. Now, I'm going to do a couple steps in one. I can write this as times e to the c, right? Times e, well, I'll just go ahead and do it. Times e to the c. And now I can take away the absolute values, and if I take away the absolute values, then I can get a plus or minus in front. And so plus or minus e to the c. If I really had this all thought out carefully, I'd know exactly where to put the e to the c right there. So that right there is going to be a constant. So I'm going to get k over mv plus g is equal to some constant times e to the negative k over mt. And now how do you solve it for v? I guess I have to subtract g from both sides. So there I subtract g, and then I multiply both sides by m over k. And again, this is just some constant, and so if I multiply that constant by this constant, I'm just going to get a constant. I can keep doing that as long as this is arbitrary. That's not an arbitrary constant. That's the value of g. But this is just some arbitrary constant here, so if I multiply it by something else, it's still an arbitrary constant. No reason to make it look any more complicated than I have to. So I'll call that A1 and just call this one A. So it's going to be A e to the negative k over mt. And now I have to multiply by g and divide by k. Let me make sure that I haven't lost you here. Okay, very good. Okay? Now, let me show you why it's okay to do all these things, calling this a constant and so on. Because in general, this is your general formula, and now it might be that you're told that your initial velocity, say that our initial velocity is I don't care, say it's equal to let's just say it's equal to 0. Let's just say we start at velocity 0. Then what does this thing have to be? So let's figure it out. So if this is the case, then what do we know? This is v of t right here. So I know that v of 0 has got to be equal to a e to the 0 is just going to be 1 minus mg over k. And that's all equal to 0. And what does that tell us? That tells us that a has got to be mg over k. So this thing right here would be just mg over k. And so it doesn't matter how complicated that was, by the time you're done, this is what you're going to have in front. You have to. Because if you're starting off with v of 0 is equal to 0, by the time you found out what this constant is, it's got to be equal to that. So there is the solution, assuming that you are starting at velocity of 0 and you're just falling straight down. Okay? So there it is right there. If you wanted to find the height, I think this is one of the problems I have in the textbook for you. How would you find the height? How did we do it before? The height is the derivative of the, I should say the derivative, the velocity is the derivative of the height, right? So here's your height. That's equal to the velocity. And so if your velocity is equal to this, then you'd have to take the antiderivative of this in order to get y. Agreed? This is v of t right there. And so now you'd have to take the antiderivative of that in order to get y, and should be able to do that. Okay, I'll leave that for you. Okay, so I think that's all by way of assuming that that the velocity is proportional, that the force is proportional to the velocity. And by the way, notice that this works whether the thing is going up or going down. Let's check it out here. If the object is going down, then what did I say? The object is going down, so v is negative. You have a negative out here. A negative times a negative gives you a positive, which means that the force is going to be up. If you have something that's falling down, the force due to friction is going to be retarding that motion, so it's going to be effectively pushing it up. On the other hand, if you have some object here and you shoot it up into the air, okay, now you're shooting it up into the air. Well, now not only is gravity tending to pull this thing down, but the force of friction is also tending to slow it down, right? It's pushing through the air like this, and so the air is pushing back on it. That's the first law of Newton's laws of motion, that for every action there's an equal and opposite reaction. If it's pushing against the air, then the air is pushing on it equally. And so the air is pushing down on it. Let's check it out. If the velocity, here's our equation right here, if the velocity is positive, and this is positive, and this is negative, then notice that the force due to friction is going to be negative. So if this thing is going up into the air, then this thing is going to be pushing down, and of course the gravity will still be pushing down. Okay? So this equation here holds whether the thing is going up or going down. This equation is this model is good. Okay, the model is good. So how can it be improved? Okay, how can this one be improved? Well, it turns out that this is true only when speeds are fairly slow. If you have something which is just slowly moving through the fluid, through the air or through the water, then you're basically giving it lots of time to kind of flow around the edges, and you're just kind of moving like this, and it's just kind of flowing around the edges. And so the amount of force that you're having to exert is just proportional to the velocity. You're just going to be moving more things around the edges as you move it. So if you move a little bit faster, you're going to be flowing around the edges a little bit faster, and you're just pushing it out of the way. And the stuff that you push out of the way is going to be, if you're going twice as fast, you're pushing twice as much stuff out of the way, and so it's going to take twice as much force to do it. Okay, should I say that one more time? If you're moving at slow speeds, then this stuff that you're moving out of the way is just going around the edges, and so if you go twice as fast, there's just twice as much stuff per unit time, which is you're forcing to go around the edges, and so the force required is going to be twice as much. However, as soon as you start going too fast enough, then you're really not given that fluid time to go around the edges. Instead, you're basically pushing it back. It's like it's there, and you're grabbing it and you're pushing it backwards. So now there's a different dynamic involved. Now, not only as you move faster are you encountering more fluid, but all that fluid that you encounter, it's not just going around the edges now. You're forcing it to back up and to reverse direction and to head backwards. And so now if you read everything I say in the book, I explain this in a little more detail, but now basically what's happening is as you double, if you were to triple the speed with which you go, not only are you encountering 3 times as much fluid, but all that fluid, you're forcing it to go 3 times as fast backwards. And so the total amount of force is going to be 3 times 3. Okay? In other words, if you start going really fast, then the proportionality, you're proportional not to the velocity, but to the velocity squared. Okay? That's what's key. It's proportional to the velocity squared. Okay? So it looks like that. Okay? So for high speeds, and I don't know, this is something that you learn in fluid mechanics and things like that, to find out exactly where that is, and it's done just through experimentation and so on. Exactly when it changes from v to v squared, I'm not sure exactly when that is, but certainly for falling bodies, falling at close to terminal velocity as fast as they can, it would be v squared rather than v. Okay, I had a friend in graduate school who got a degree in aeronautical engineering, and then he went back to Orange City, Iowa to work with his father on developing an airplane for missionary use. And they wanted an airplane that would be able to go into the kind of the deep, dark areas of the globe that most airlines can't get into, where you have maybe jungles and not much area. So you want a short runway space, and you wanted 2 engines for safety in case one engine knocks out, and you also wanted a high payload. You wanted it to be able to carry lots of stuff. So they developed an airplane over about 40-50 years in order to do all that. And at one point, they had one built, and they had this airplane. Here's the airplane, and here's the propeller, and actually the propellers were on the wings, I guess. But this thing was rumbling through the air. It didn't go as fast as they wanted it to, and it was a lot of vibration. And so they took and they put a whole bunch of little stickers on it, a whole bunch of little pieces of just paper that they glued on one end, and then once it was up in the air, they could see the wind patterns. And a lot of this paper was flowing backwards, so there was a whole lot of turbulence that was going around and things like that. And so they went to Iowa State, where he got his degree, and they changed the model, they changed the fittings for the engines and so on, and they found one where all these things flew back very nicely, where all these little pieces of paper just streamed straight back rather than doing all this crazy motion where they're going forwards and all sorts of turbulence. And so they changed they changed the cowlings around their engines accordingly, and sure enough, all that vibration stopped, and they got an extra 40 miles faster, miles an hour faster. So it's all an example of what you can do with modeling just by actual experimentation. So it's kind of cool, Okay, so so anyway, let's go back to this. So let's see if this makes sense. Let's see. Here we are. dv dt is equal to negative g minus k over m v squared. Okay? And let's see if this makes sense. Well, let's see. If the object is moving, up, then v is going to be positive. And so since v is positive, v squared is positive, so all this stuff is positive, and so if it's moving up, the force due to friction is going to be going down. That's what we want. Of course, this is down, so both of these forces are going to be down. That's what we want. On the other hand, if the object is moving down, then v is negative, but v squared is still positive. Agreed? A negative number squared is still positive. So this is positive, this will make it negative, and so that's saying that if an object is moving down, the force due to friction is also going to be down. Oh, we don't want that. If the object is moving down, we want the force due to friction to be up. So apparently this is not really what we want. It works well when v is positive, but not when v is negative. Okay? So this is where, when I teach the class, I give them a lot of time to ponder this. If you're game, you take a moment and shut off the video and see if you can figure it out before I give it to you, but I'm going to do it right now. Okay? It turns out that the easiest way to write this is something like this. Okay? There you go. Now notice that when v is positive, both of these things are positive, and so the force due to friction is going to be negative, which is what we want. On the other hand, when v is negative, then this is still positive, this is negative, and here you have a negative there. Negative times the negative is positive. So sure, now if velocity is negative, the force due to friction is going to be positive. So this is what we want right there. Okay? So, how would we solve this differential equation? Okay? You could do it. It's a separable one again, but it's going to be kind of a messy one. It's going to be kind of like the one with the what's the one we did with carrying capacity. It was pretty messy. So instead of doing this one all with the separable dE, let's instead just be satisfied to do the phase diagram. Okay? What would the phase diagram look like? In other words, what if you have this? Y is equal to, let's just do an example. -5, or say, I don't care, negative 4 minus x times x, like that. What would that graph look like? What would that graph look like? Okay? Something you haven't done. Let's first do this one. -4 minus x squared. What would that graph look like? Do you agree that the vertex would be here at -4, and it's going to look like this? It's going to be pointing downwards because it's going to be a parabola. It's going to be going downwards because you have a negative x squared. On the other hand, if you had a plus x squared there, then it would look like this. Agreed? Then it would look like that. So what happens if we kind of do both of those and we have x times the absolute value of x? Well, notice that for positive x, it's going to be just like x squared. And so it's going to look like let's see, I guess I have a negative there. So let me put a negative there. Okay? So if x is positive, okay, right here, x is positive right there. This is your y right there. If x is positive, you're going to get positive times positive with a negative. It's going to be negative 4 minus x squared, which is going to be a parabola going down like that. It's going to be that one. On the other hand, when x is negative, now the absolute value of a negative number is the opposite of that number, right? If x is negative, then the absolute value of a negative number is the opposite of that negative number. So if x is negative, which is over here, this is going to be negative. I'm sorry. Let's see. Let me do it again. If x is negative, then this is going to end up being, let me write it like this. Okay, here. Y is equal to negative 4 minus x times x. And so, if x is positive, then this is just going to be equal to negative 4 minus, if x is positive, the absolute value of x is the same as x, so it's going to be x squared. So it's going to look like this. If x is negative, then the absolute value of x is the opposite of x. So it's going to be negative 4 minus x. Now the absolute value of x is going to be the opposite of x, so it's going to be negative x right there. And so that's going to be negative 4 plus x squared. So it's going to look like that. Okay? This takes a whole bunch of thought. Okay? I'm kind of going through it somewhat fast. If you were all here in the class, I'd have you all doing this on your own, and we'd be taking lots of time for it. But the point is, that's what the graph looks like. It's this parabola for this side, and it's this parabola for this side. And so now it's going to be the same thing if you have it here. If now let's get rid of this. Let's just change it so that this is v, and this is dv dt right there. And this right here is negative g right there. And so now we can use this thing to determine what's going to happen if something is dropped or thrown up or anything else. What happens to it? If something starts with a positive velocity, well, look at what happens. If it starts with a positive velocity, what does it do? Remember how you use a phase diagram? You look down and you say, oh, this is negative, which means I have to decrease. I'm going to keep decreasing. Notice I keep decreasing until I get there. On the other hand, if I start with a velocity, a large negative velocity, let me make that a little bit like that. A large negative velocity, then what? dv dt is positive. Since dv dt is positive, that means I need to move in this direction. So no matter which, it doesn't matter what the initial velocity of this thing is, it's going to eventually end up going at that velocity right there. And what is that velocity? That's where this thing, let's see, we're assuming that v is negative there, so it's going to be negative g minus k over m. Since v is negative, the absolute value is going to be a negative v times v. And we want to know, when will that whole thing be equal to 0? So notice I'm going to get negative g plus k over mv squared is equal to 0. We solve that for v. What do we get? We get v squared is equal to g. I can go ahead and multiply through by m, divide both through things by k, and then I can take the square root of it, and it's either going to be the positive or the negative. Obviously this one is the negative right there, so it's the negative square root. So there is your terminal velocity. No matter whether if you shoot something up out of an airplane and it's going up really fast to begin with, or if it's going down really fast to begin with, or if you start at a velocity of 0, no matter where you start it, the terminal velocity of this thing is eventually going to be falling at this speed. Okay, if you fall out of an airplane, eventually you're going to be falling at that speed. Let me make sure I caught you again. This is a long video. Yeah, very good. Okay, so you're going to be going at that speed. So that's your terminal velocity. And notice that it makes sense. The more massive you are, the faster your terminal velocity is going to be. If you throw a brick out the window compared to a paper bag, the brick is going to have a much larger terminal velocity than the paper bag. It also depends on the gravity. Okay, with the Earth's gravity, if the Earth were pulling down at twice the amount, then the terminal velocity is going to be greater. And K has to do with basically what the frictional constant is, right? It kind of depends on the size and the shape of it and things like that. But if the shape of it causes there to be a whole lot of friction, then the terminal velocity, notice, is going to be less. If K is very large, then the terminal velocity is going to be less. So this is kind of your amount, the amount of friction. Okay? So as soon as you get any sort of a answer like that, you need to check it out and see if it makes physical sense. Okay? See if it makes physical sense, and sure, it makes sense that those two things are going to make the terminal velocity greater, and this thing here is going to make the terminal velocity less. So there's your terminal velocity right there. Okay? So what I didn't do for you was I didn't use the phase diagram to get the terminal velocity of that original one. And I think that's one of the exercises, so that's for you to do. But you can do it the same way as we did this one. Okay, lots of good stuff there. And this is all stuff that's very important for falling objects. If any of you are going to be doing anything in modeling, where you want to model objects going up and down, balls, soccer balls, things like that, this is all stuff that you can do. In fact, I had once when I was at Hope College, then I was going in to play racquetball, and the women's volleyball coach asked me, she said, "Can you help us figure out how the women and the women's volleyball team can serve the ball so that it obviously goes over the net and then comes down as quickly as possible on the other side of the net? You don't want it to take too much time because it gives them time to react to it, and you don't want it to end up way back here because then it's easier to bump it back. So you want it to go vroom like this, okay?" And so it turned out that my partner that day playing racquetball was a retired physicist from NASA, lo and behold. So as we were playing racquetball, we were also discussing the problem, and we decided it was a bit more important, more involved than what we could do while playing racquetball. I think I won that day. So I ended up giving it to a couple students that summer, and we spent the summer working on it. And it turns out, as you would expect, that the motion of the ball depends on gravity, it depends on air resistance, and it also, can you guess what the third important factor is for getting that ball to do this? If you ever watch David Beckham or others shoot a soccer ball, they do the same thing. They want that soccer ball to go over all these people that have their hands up, and they want it to go into the net, and they want it to not go like this. They want it to vroom, go up and come back down. So they put a top spin on it. Same thing here, you put a top spin on it, and that top spin will cause it to go up over the net, come back down. So the point is, as we were modeling this thing, we made our model, and then we actually had a little volleyball cannon that shot volleyballs, and we were able to take all the measurements, and we compared the actual picture of the volleyball in time-lapse photography to what our model predicted, and those things were basically right on. So really kind of cool. the way our model did a really good job of predicting exactly where that volleyball would be coming out of that volleyball cannon. So the point is, you can get good models by using this sort of thing. And if any of you are going into game design or something, this is the kind of thing you can use for developing games that are very realistic, because they show something that slows down as it goes and that sort of thing. Okay, very good.